Hello everyone. Today, today we'll learn about the chemistry's application, especially the inorganic chemistry. Last time we read about the physical chemistry and organic chemistries used in everyday life, right? Today we'll learn about inorganic chemistries. आपने देखा होगा many professors, many students have spoken about inorganic chemistry as like you mug it up. And generally we don't see the purpose of learning inorganic chemistry in everyday life, right? But I'll tell you why we don't see that, and why we see physics concepts being used in daily life and not chemistry. Because physics deals with macro problems, right? Which are naked eye, which are everyday experience with forces, momentum, energy, electricity, and other things we can see easily and comprehend uh, and, and apply the concepts of physics into daily life, and that becomes interesting, and that's why our mind can memorize it, the concept well, because it sees that in our daily life it's getting used. While in the chemistry, and especially the inorganic chemistry, we see no direct applications, and that's why we we don't tend to memorize it, because chemistry specifically deals with the micro objects, tiny, like what happens inside the molecules, how things interact at the molecular level, right? So today I'll bring one daily use life and show you how you can use inorganic chemistry in your daily life. And if you build that conceptual understanding about inorganic chemistry, then you can see your life in a different lens, from a different lens, right? So let's talk about one situation is that poisoning, chemistry of poisoning, chemistry of poisoning. What happens if you have heard about cyanide poisoning, potassium cyanide to be specific, right? Why is that cyanide attacks? Why is cyanide poison, right? Let's understand what happens in our body. Sorry for the diagram, but in our body, to survive we need oxygen, right? Why we need oxygen? Because you have you have read about the how oxygen and our carbohydrate, I'm just writing the simpler form, it's more complex, react with O2 and gives the metabolic energy we need to survive. Our every cell, it needs energy to survive, and we release CO2 and H2, right? Now, this is very primary reaction, and if this reaction is stopped, our cell starts to die. And if our cell starts to die, we can't live. The life is not defined there. So what happens? What happens? How this oxygen reaches to the glucose? Yeah. So what does? We take O2, inhale O2 from our nose. It goes to our lungs, and then lungs pumps it and mix it with blood and circulate via veins and everything to our every cell, every part of the body, and every part of the is that it hinders this basic metabolism function, basic life function. What it does, so before that I'll explain how this O2 mixes in the blood. So blood has this hemoglobin, Fe2 plus, and it makes a coordinated bond with something, some compound, okay, and this whole is called hemoglobin. What O2 does is O2 have the electronegativity greater than this compound, let's say this is called B, right, and it replaces this and makes the coordination bond with O2, right, or covalent bond to be precise, I think metallic bond, okay. So replaces this and makes a bond with O2. So and then in cell there would be a mitochondria where there is the energy house, ATP house, and when blood has this O2, this the insulin, whatever we eat, that liver gets that get converted into glucose and insulin plus that sugar and glucose in mitochondria, and this O2 is taken by here, and then this reaction happens. But what happens when cyanide comes, let's say with potassium cyanide, what happens, cyanide is very electronegative and its electronegativity is more than O2, and it replaces O2 from here and makes bond with Fe2 plus, which hinders the O2 coming into cell and received by OTP or ATP, and then this lets the body dead. Slowly every cell gets died, like brain dead, and person is dead. Same like O2, CO also have this carbon monoxide have the electronegativity greater than O2. There are other electronegative compounds. If somehow they are delivered to the body, they can replace O2 if they have the electronegativity is greater than O2 and makes a bond with Fe2 plus. Generally, it's this coordination bond which we study in the coordination compound. Now, if let's say person by mistakenly or intentionally been given to the cyanide, how he survives? For that, what doctors do is that they uses physical chemistry and inorganic chemistry to treat that. How? They'll ask you what amount, firstly they'll assess what amount of cyanide or CO or any other electronegative compound have been taken, at what time also. Through this, they'll find out how much quantity of antidote to be given. So they uses both equilibrium and chemical kinetics and maybe thermodynamics concepts, thermochemistry concepts, and find out the quantity. How thermodynamics concept is the temperature they take of the bodies as 37 degrees centigrade, right? This is reaction place, and the quantity and the time. Here they use chemical kinetics rate, how cyanide reacts, whether first order or second order reaction happens, and through equilibrium quantity they can find out the quantity using all those physical chemistries, mole concept and all those solutions concept, right? And how they select the which antidote to be given? Again, if CN or CO or any electronegative poison had the electronegativity greater than O2 and attacks to Fe2 plus to make bond, same how they give something like hydroxocobalamin, which has higher electropositivity than Fe plus, and it attracts CN or whatever the poison element and frees the Fe2 plus, which again starts reacting with O2 and delivers the basic biomechanics reaction, right? Now, why see there are other metals who have highly positive K plus, Na plus, or there are other, why not to give except this? So they are given in form of sodium carbide and nitrite, and there are others. Even nitrites can be used as one of the electronegative compound to poison. But what happens if you give free metals? They can oxidize some of the tissue, right? And they can damage. They'll remove the CN, but they'll damage. While this hydroxocobalamin reacts with this cyanide component and makes the bond with cyanide, and this is nothing but becomes vitamin B12, which can be extracted out through urine or through excreta, or it can be digested. So we have to use the antidote which cannot be having more side effects on the body. Okay, so you see in this poison chemistry, using the biomechanics and physical chemistry, inorganic chemistry, we can really, solve the poisoning chemistry, we can save lives. So there are other applications of inorganic chemistry, why life chooses silica to make enormous amount of inorganic compounds, and why carbon, to, well, they are into the same periodic table. If you follow, they are from same periodic table. They have the maximum valency bond, so so carbon becomes more flexible for organic compound, silica becomes more flexible for inorganic compound. Having the ability to make larger bonds, they can pass the information more easily. Bonds are nothing but the information passing mechanism. Okay, we'll see more examples in a couple of upcoming videos, how to use chemistry in daily life and how to learn those concepts and how to apply those concepts. Thank you for watching.